is higher. But we evaluated the models independently. So we took the eating model and the sensor readings, and the eating model returned this curve, and we took the sleeping model and the sensor readings, and that's what the sleeping model returned. That's why we then had to use that decision engine.
Okay, each time you rebuild your model. So this model is not fixed, and you don't decide only this time, but from sensor reading, you rebuild each time, each model.
Yeah, not rebuild, but reevaluate. We do the evaluation for every trace and every activity model, but then we have to lump the activity models together to decide which one was most likely in that time frame. Now, the eating model might not have contained specific times for eating, since that varied during the day. It was sometimes breakfast and lunch and dinner. It was not as easily determined when you just have the activity and the break. Let me go up a little bit. Yeah, this one. Slow. Yeah, okay. When we have the model, the eating activity might have different break behavior. So we have in between, let's say in between breakfast and lunch, we have 3 or 4 hours break, or 6 hours break. In between lunch and dinner, we have a longer break. And in between dinner and breakfast, we have a 12-hour break. So in the model, sometimes it evaluates, okay, if you went through that area after 3 hours, it might have been a short break and you might have gone back to the activity. So that's what our model evaluates, but the highest probability, again, falls to the sleeping activity at that point.
You have an independent model for each.
Yeah, because it's easier to compute and also way easier to build and more flexible, including and excluding activities.
So it's targeted for nursery homes and such places where people behavior does not vary so much.
Yeah, it's not necessarily nursery homes, but elderly living environments. Yeah, not nursery home yet, where you have the active monitoring.
Thank you very much for your presentation. I had 2 questions. In your decision tree, you deleted some branches based on, for observing one sensor is not doesn't have anything to report. Is it again a probability or your 100%? I mean, is there a threshold to make this decision? Because it's very important. The rest of your model is probabilistic, but this one you just say we delete this one. I can't understand. Do you use any threshold for that?
So for the deletion right here,
yes,
we do not use any threshold. So if we are sure that this behavior cannot match or this trace cannot match that behavior, then we delete the branch altogether. We only delete the branches where we're sure that they do not match this branch. And so if we have no observation in the kitchen area and necessarily for cooking, you need someone in the kitchen area, then we can delete that branch, for example.
And you mentioned you used a non-Markovian model.
Yes.
So how many states have you assumed?
We do not explicitly build the model, but the method does that on flight. So we really start with one initial state and then step by step discover that state space. So we do not have to bound the state space, but it happens automatically in the building process by either cutting off a time, and which I didn't mention, we have a cutoff probability. If you have a branch that falls below like 10 to the minus 6, 10 to the minus 9, whatever the cutoff threshold is, that becomes very unlikely. Then we also prune that. But we do not build the whole expanded state space model explicitly. That's one upside of the method.
Have you checked if you use a Markovian model instead of having memory, just use a zero memory, then how much your accuracy increases?
Not in this case, but we've been working with this method for a very long time. What we can also do with the Markovian model is to look at the long-term behavior. What you cannot capture with a solely Markovian model is this wavy behavior that is more likely now to be in the kitchen or less likely now to be sleeping. That cannot be covered by a Markovian model.
So did you consider or did you compare this also to a learning-based approach?
We compared it to literature. We do not have any implementations of learning-based approaches. That's why we use an existing data set to be able to compare it to other people's usages. And We have in the paper also, we looked at some deep learning based approaches. They're more expensive in creating the solution, but very often they're also more successful in the actual matching process. But they have a completely different approach. Usually in a deep learning method, you're assuming you have a black box model that you train, or you have a pre-trained model that you adapt. Whereas here, we figure that when we have the system information, we should use it in the modeling process. So it's an alternative method. It's not necessarily that you should either this or that, but it depends on the application.
Then just one, because the sensors you use is basically, so would you agree this is basically you are predicting the location of the subjects? I mean, you say they are eating, but essentially you know they are in the kitchen. Right?
In this case, yes, but there's also settings where you have faucet sensors and cabinet opening and closing sensors. The method doesn't really care, but in this case, probably yes.
Yeah, okay.
Close this talking point at 100%.
Right, so thank you very much. So we have a few more minutes. This is coffee break. So you can enjoy coffee break in the next 20 minutes. And then our keynote speaker, Professor Cecilia from, is it okay, the pronunciation? If not, then I can ask some of the people. Yeah, thank you. So she will deliver her keynote speech and we'll enjoy her talk. So please come and just enjoy some snacks or coffee, please. Thank you very much. And if you need anything, that this volunteer can help you. More? All right, so. Yeah, please go ahead.
Hi, thank you for you're here.
Ieri quando stavo facendo il talk.
It's related to the last So is there any constraint that you follow? Whether if it's, for example, if this is the bed,
So much, no, not at all. We just did statistical analysis of what sensor is related to what's label activity, and we had not looked at the actual layout. We are another activities on a generic basis, whether the residents engaged in activity or not. And the individual models was, for example, the skiing activity, because that was so that was a little more intricate.
so it's not that I mean, two things. So
We didn't consider that. We just considered the time depending behavior in the activity.
Magari aveva più senso farne di meno adesso.
As in the sandwich, I don't have the lunch and my Oh, maybe as
Professor Cecilia Mascoro here already, and she is, I will introduce her. Oh, by the way, I'm so sorry, no, sharing this session. And yeah, I will read her bio, but she is studying the right here, saying that she is a mother of a teenage daughter. I'm a father of a teenage daughter.
very difficult for you.
It's easier than what I. No. Okay, let's talk at the panel. Okay, anyway, so she's a full professor of mobile systems in the Department of Computer Science and Technology, University of Cambridge, UK. And she is the director of the Center of Mobile Wearable Systems and Augmented Intelligence. And she is also a fellow of Jesus College, Cambridge, and the recipient of ERC Advanced Research Grant. Okay, so she has a long CV. So yeah, she can also introduce by herself. But she had so many big, publication and also achievements. So okay, we are very much excited to hear that. Yeah.
Please welcome Professor Cecilia.
Thank you for this invitation. I'm really excited to be here, and I hope to make the talk a little bit more entertaining. I feel challenged by the range of age of the audience. I'm not sure I can entertain the youngest members here. We'll do what we can. So thank you very much. So we have seen that the world is now full of these devices we wear, and they're sensing our behavior through sensors, new sensors, and they're sensing also our health. So one might think that us as academics, I'm talking to mainly academic researchers in the room, that the research in applying these devices and using them for health has been solved, and that we should pack up and move to different topics. In the reality, this is not true. And in the next slide, I'll show you what I think are still the challenges in this area, and why I think there's still very much a lot of academic research to be done here. I know companies have taken these tools and brought them to commercial use, but in most cases, we don't trust them. In some cases, they're not good enough. In other cases, they don't do what they could do. And so we're here to push the boundaries. And so the talk will touch some of these aspects. And I'll describe all of them right now, but then some of the aspects will be in depth with some examples in the talk. So there are many sensor modalities that have not yet been explored. There are, for example, sensors already embedded in some of these wearables, hearables, that we have not tried to use to monitor health more effectively or efficiently. And there are obviously other sensors that have not been built, have not been tried, or maybe don't have yet the efficiency that is needed for certain form factors. For example, in Wearable, people are trying to put the EEG around the ear, but we're not there yet. So there's still quite a bit of research in the hardware-software part of the work. We often do not do very well in analysis of continuous signal and longitudinal signals, and matching it to possibly diseases and health. So my conversation sometimes with a clinician has gone from saying, if I gave you, for example, audio signal from the abdomen constantly to a device, what would you be able to do? And the answer to that question is not straightforward, because they are not used to diagnose from that sort of signal. So the leap from going from the type of signal they have to the type of diagnosis and analysis they can do is something that we need to work together to solve. And to me, that's a very interesting problem. Most of the analysis that we do, both in academia, but I think also in commercial environment, does not include free living. Now, when you do activity recognition, you know that labels are important. Labeling large quantities of data that are of people in the wild is something very difficult. And there are now techniques in machine learning that are trying to obviate this problem. And I will talk a little bit about that. So the ability to use this sensor for interpretation of behavior in free living conditions, I think is still a big challenge at scale. When we do interpretation of results, you go from sensing to a classifier of whatever it is, a more modern thing, let's say even a deep learning neural network, then usually the aim of that for most of the, community and even in the machine learning community is accuracy. Is this more accurate? Does it beat the 95%? Does it go to 96? But one aspect that is very important in health, and certainly one that could bring together doctors and researchers in machine learning community, is actually knowing if that accuracy is confident enough. If you're really sure that that is what it is. And there's this whole world of uncertainty. I have a few slides on that if I get there. Then the elephant in the room, data privacy. We are collecting data that is quite sensitive, and even with the 2 or 3 points of GPS, we know that we can possibly correlate the data with another data set and know who that person is. So what do we do about that? My solutions as a computer scientist systems researcher is to try to build more and more on the edge, try to show that things can stay even on smaller devices, that you can push models or part of the model more on the device of the user so the data doesn't need to leave. And I have a few examples of that. And this is very related to computational efficiency. When we do this sort of analysis again, the machine learning community is not concentrating on trying to make things and models efficient that much. I mean, there's a whole line of work now on on-device machine learning, but working together with the idea that we have wearables that have a certain form factor, they have certain very limited MCUs is very interesting. This is related to data privacy because if you start to do things on device, you're able to do things, if you're able to do things efficiently, then you're able to keep the data closer to the user. So I know I talked a lot about one slide, and now I will go through a set of examples of research that we've done. Now, cardiorespiratory fitness is an indicator of our cardiovascular health, a very good one that is linked to, inversely related to many negative health outcomes. It's actually more correlated than looking at cholesterol, looking at diabetes. So this is a good number that someone would want to have about health and behavior. However, it's quite difficult to get that number. How many of you have been put on a machine like this? Let's see how many athletes we have in the room, many fit people we have in the room that have tried this VO2 max test, as it's called. I'll explain. Not one? I usually have at least one in the room. So this is a very pushy test where the doctor will tell you, go on this machine, it's either a treadmill or a bicycle, and they'll tell you to go to your limit. And they will measure your heart rate, but they also put a mask that measures the amount of oxygen essentially that your lungs are able to breathe in and breathe out, and this essentially informs them of how much of oxygen you would be able to transfer to your muscles and then transform into energy. That's the principle from a computer scientist of what's happening here. So this is not a test that scales. One, because not all of the population can go on a treadmill and go to the limit without some strange health outcomes. And two, because it's expensive on the number of people you might have to run this experiment and do that. So there's the obvious thing that you will want to do automatically through devices. And in fact, some of the devices are already doing it. If you have an Apple Watch, for sure, I'm sure also there are other devices that do it, but I'm very familiar with Apple Watch. So they measure your VO2 max already. However, the way they do that, from what I understand, is that they often do that on when you're very active. So I'm a runner, and so they kind of are able to use that information. Do it in a situation where you have information about your full life. If you're not a very active person, is another story. Is doing it in free living conditions without labels is actually much more difficult. But obviously, I'm sure Apple is working on that, and so are we. It's a very interesting problem. So we know that it's one interesting aspect. So we happen to work with, this paper is just out. It's just been accepted. It's already on archive. If you want the title, you will find it. But it's not being pushed out by digital medicine, but you can find the paper. So this is done with collaboration in epidemiologists. They have done a large study where they tracked 10,000 people, and 10 years later they tracked 2,000 people, let's say. What did they collect? They collected this VO2 max test. I note that they didn't quite collect the gold standards. They didn't put all these people who share a very distributed age all on the treadmill until their death, essentially. They stopped, and then they have a way to approximate the last bit. You can ask me more about that. But let's say they have a VO2 max test. They have some anthropometric measure, and they ask them some questions. But they also, for 6 days, tag them with a movement, a watch an accelerometer on their wrist and a chest band for their heart. So you have all this data, and what we've done essentially is trying to use some very basic neural network, 2 layers connected network. We feed the extractive features from both the movement and the heart, and the question is, can we predict the fitness? That's one question. The other question is, can we infer the fitness after 7 years? This is a very difficult question. The answer is no, we could not infer the fitness after 7 years. What we could infer was the direction of change of the fitness. If someone was really going to change dramatically after 7 years, we had a good indicator for that prediction. So, which is actually probably the most interesting bit. That we could tell, oh, this guy, given how it's going, is likely to be at risk of changing dramatically. And the system seemed to be able to distinguish that. This is something we're still digging because I think it's a very interesting question. We also tried to see, less important, in fact, I won't talk about that, to see if the model that we developed on this cohort was actually predicting okay on this cohort. These are the 3 things you can find in the paper. I'll give you a couple of slides on the graphs. I won't talk much about the technique. So this is a logistic regression task where we should, let's look at graphs just to try to keep it light. You can go and look at the numbers and ask me questions about the numbers later, but let's look at this graph. This graph shows the distribution of the VO2 max, so this cardiovascular fitness value, for the true people. So the true distribution is the blue line, and how our predicted model does it with the predicted, with the model. And so what we see here is that this is the error, right? We underpredict some of the cases. When the VO2 max in a certain range, we tend to underpredict them. And that's one of the findings. The other thing that is interesting here is that we tried to see how predictive the measures of resting heart rate and anthropometric square, and how much the wearable was adding, because resting heart rate is already very, very predictive per se. If you know a person resting heart rate, you're likely to be, it's very correlated to your fitness. And so how much, I think you're drawing on the screen by this.
Is it coming? No.
Yeah.
I'm not drawing it.
I mean, it almost looks like I've drawn this, but I have not. But anyway, this shows that by adding the wearable data, you get a lower error. And here you might ask, but does it really matter to have that additional lower error? Is not much if you think about that. Well, speaking to the epidemiologists, it turns out that for some of their questions, even just increasing just a little bit, it means that they can answer different questions. So it's actually worthwhile looking at what you can achieve and when you have your best performance. And this is the part that I like. It'd be good if this circle went away somehow. That can be arranged. You think we can take away the circle?
Just maybe you can stop the presentation and restart it.
Yeah, that's true. Yeah, I was trying to avoid that.
No?
Yeah. No, let's stop share. Yeah, others.
Because my laptop, I don't have Wi-Fi. I disable it so that nothing comes.
So, but I how do we avoid that this happens again? Who's drawing on my screen essentially? So this is again the same problem, different graph. On the x-axis here, we have the difference between current and future VO2 max. So this is the kind of ground truth somehow. And what we can see, this is the sensitivity specificity ROC curve, AOC curve. And here, the green curve is the one of where the change has been higher. In the case of the change being higher, we are able to predict that better, which means we're able to predict big changes, but not small changes in the 7 years period between the VO2 max of the people when they are 7 years younger and then 7 years old. And I think this is a preliminary result that we want to look more into, but I thought it'd be interesting to talk about that. Yes, I think so.
I mean, to predict which data do you use? You use
We use the heart and we use the
7 years
movement.
before data, or
Yes.
the heart data after 7 years?
Yeah, we also try to use the heart data after 7 years. Yes.
Predict the VO2.
We've tried various things. So I think I can't remember which curve corresponds to which test that we've tried, but the paper should have all the details. But that's a very good question. You should answer it. And then with the same data, so I'm moving on from that paper, with the same data, we tried another little experiment, which perhaps is interesting because the next few slides are about using different architecture, using different techniques of machine learning on this sort of data. So here we tried to use the same input data, so the activity, CNN, RNN to consider the temporal aspects because we'll put in time as well as the heart activity, and then and the activity, and then predict the heart. That's the main task. However, we are using this task in parallel with another aim, which is to predict demographic and relevant information. So what we do is that at the penultimate layer in this network, we consider a latent representation and use that to feed it into a linear model that can predict use. So our main task is heart detection, but with embeddings, we spawn another task that is able to predict these things. So the result is, can I, with that network, predict these things just from the activity, temporal, and I will show you resting heart rate data, and the answer is reasonably well. And here's, again, the paper you find on my webpage. And these are just a few results. Let me perhaps explain what these numbers mean. This is, we use just acceleration data and the time, acceleration data and resting heart rate, acceleration data, resting heart rate, and time. The mouse is distracting me, and this is the embedding results. So when we train the classifier on the embeddings in the latent space, and then try to, PCA to reduce the dimensionality of our features, but then these are the measures: physical energy expenditure, height, weight, sex, age, and BMI, with a reasonable results. Some cases not very reasonable, but you can think there is a signal here that can tell you just by examples of activity, resting heart rate, and time is able to tell you something about the person, which is, I think, very interesting. But I'm happy to discuss later, perhaps. Again, when you start having, like we did, we have this beautiful data set with lots of unlabeled, the heart rate and movement data of those 10,000 people is not labeled. We don't know what activities they're doing. So one question might be, and that's the one I'm trying to answer. There are many other questions. How do we label? I'm not answering that today, at least I'm not answering that partially. But I'm answering a different question, which is, can the use of unlabeled data be useful in our activity prediction task in perhaps HAR data sets that we have as a community considered quite a bit? And that's the question I'm trying to answer today. And in the next two slides, I'll give you an example. So because I've already described this large data set where people are, we have activity and we have heart data. Can we use it? And I will explain this. I know this is like, whoa, too many boxes here. But this is an example where we do this. I'm going to use my mouse. Let's see. Yes, I can. Okay, so here is a labeled data set that we have that the community have used. Could be HAR, could be many, right? We have many data sets the community has used. I'm nodding, thank you. And we have certain performance on that. We've tried various deep learning models, but the problem is that there's not much data there, and our performance are often capped. We can't reach very good performance very easily. And so here we have leveraged the existence of this very reasonably large unlabeled data set by constructing a framework, an architecture that allows us to feed it in somehow. And so I will now go through, and this again is a paper we published last year, and it's on my webpage and everywhere else, so you can find the details. So I will now go from this architecture. In the next slide, you will find the 1 and 2 component, and we'll talk about them. And the next slide, you'll find component 3 and 4. So I'm not going anywhere. I'm just zooming in a bit. So what do we do? Well, imagine this is HAR. HAR, for those of you, how many of you know this label, this HAR? None of you? So HAR is just one of the existing publicly available activity recognition data sets that the Ubicom community has been using. So some you know HHAR, you're nodding. So, okay, right. So we have the data, which is accelerometer, and we have the labels. So this has been labeled, right? We know that. But we have a certain bound on performance on this data if we apply traditional machine learning. And so we split the data in 2 sets, but the important thing is that we take some of this data with the labels and do what is obvious. We train a deep learning model to recognize that data, okay? Simple. Until here is just tradition. But then we use this model on the data, the big data that I had for the other study, the cardiorespiratory data. I've been talking about the data until now. So we use the model to predict labels on that data. Remember, I don't have labels, so I don't know how good my prediction is on that data, right? I know nothing. So here it is. Now I have this data, but I forget, we also use some other data, but let's say we go from here to here, train this and find some labels. How much do I trust those labels? Different domains, not much. So what do? We just look at the confidence in the prediction, use the softmax, use some uncertainty estimation, and you keep just a portion of the labels. You keep the ones that we think we are more confident about. And you ask, why is she doing that? Is it the aim? No, this is not the aim. This is just an intermediate set of things that I will use. Remember, my aim is to improve the performance of how we predict labels for our original task. The problem of that task is that by using large-scale machine learning, we are capped by the performance because we don't have enough variety in the data. And therefore, we need to add variety. And this is how we add variety. We use a large unlabeled data set to add some variety that will perhaps help in building better performance. I hope I'm not lost most of you. So this is the part that comes down. So from that big unlabeled data set that I then labeled, I take that and I do some more augmentation. I add transformation. So somehow I try to flip the data, I try to negate the data, I add some noise to the data, and I have the labels. So I create this augmented data set, which is even bigger now. And then I built another task that is essentially multitask that is trying to predict if the data has been flipped, if the data has been added noise, and a multi-class task that is still an HAR task that predicts the class. The aim here is to see if by training the model this way, I learn something that helps me really predict the class better. The intuition is by doing all of this, by doing all these transformations on the data, by adding more data, which is the step I've done before, I'm making a model able to adapt to changes that weren't quite in the original data set as much, represented as much. That's the intuition. Then I take this part, so I freeze some of the layer, I take this part that was the classifier of the activity, and then I feed the data that I want to try. So I'm going back one slide. Remember, I kept some data for testing here of our data set. Our aim is to try to see if we improve performance of that data. And then I feed it in there and see if I get better performance. And this is a result of performance. On the x-axis, we see how many samples per class do I need to have, labeled, do I need to have to achieve good performance now. So, labeling is expensive. And can we have good performance with a very low number of labels, for example? The blue line is what you would expect, a fully supervised machine learning approach. These two lines are an ablation study of seeing how much the transformations help, and they do help. Even there's a paper I can point you to that just use the transformation. Transformation really help. Just trying to augment the data with different noise, different flipping, different negation helps. And then here's the full approach that can also help in this case. And the interesting bit, how much it helps in the low data regime, low labels regime. So I think this line of work, yeah.
So I think that it depends on the some number of sensors or number of dimensions or something like that. Fine.
So we only use, I think, the one accelerometer. I can't remember the HAR data set, how many, you mean in the various positions? I can't remember. I think we tried to use just a data set that had a similar, but that's a very good question. I can't remember what we did. In the large data set, we know that we only have one sensor. So it's only one accelerometer on the wrist. Now, I know some of the data sets have more than, like they have 2 or 3 or 4. I don't know which one this corresponds. We certainly have tried them all. And it'd be interesting to have a comment on performance when perhaps this data is not quite collected from the same place. Are you?
No, I mean just a dependency on the dimensionality, because you are somehow increasing the number of data or something.
Yeah, but I think I'm increasing the type of things that it's not just, I mean, with augmentation, we're also increasing the type of noise that you can have in the data.
Yeah.
With the other thing, I'm certainly increasing the amount of similar data that you can have. Yeah.
So if you have, for example, a very high dimensionality, like vision or something like that, then we might work very hard on this kind of thing.
Yeah, it might be. Yeah, definitely.
So this graph might change. So
but this is for, I mean, for images, I think these approaches have been tried. It's just on this kind of behavior data that they've not been tried. And I think for images, it's probably, I don't know if it's easier to label, but certainly for HAR, because it's a continuous behavior of people, it's very difficult to label. So I think we have an even bigger problem with this sort of data. I don't know if I'm answering. Yeah. Yes, speak louder. Yeah.
Yeah, no problem. So it's a really nice idea to use unlabeled data, and it's, because labeled data are small and expensive to do. But if you don't mind going back to slides, so essentially you're using the trained model, the teacher model, to select what are the.
Sorry, I lost the second part. I'm using the teacher model.
Yes, the teacher model to predict the labels for the unlabeled data, and the goal of this is to increase the variety of the data that can improve the original model, essentially, right? And it's nice that you apply the filtering to select the ones that you trust the label is maybe okay, but does that limit the data in a way that you're choosing essentially quite similar data that the model knows already, which maybe didn't really help with the overall data?
We had that hypothesis because I expected higher improvements with respect to the transformations. If you saw in this graph, we do have an improvement over the transformations, but in some cases, there is not much improvement. So it looks like, especially when you have few labels, the transformations do quite a bit of the work already. So yes, I think you're right that by choosing that probability, you're probably keeping something that the model can predict very well.
Yes,
it's absolutely true.
Yeah, so and then it's just, I think it's interesting how you can increase the variety of the examples as well as to make sure the labels are correct at the same time. I think that's what you want to get out of the unlabeled data essentially, but I think it's difficult. It's difficult to do.
It's difficult, and I think I need to ask my student, but I think we tried to play with that confidence.
Yeah, because if it's so high, then the model knows this type of data already.
So here is a parameter. You could try to see what happens if you let more samples through, more of the data through. I think we have tried. We probably chose the best one for the various things, as you would imagine. But it's a very good point. And thank you for understanding fully what I was explaining. This was very, very good. So I'm shifting a bit in this last part of the talk on something that we have done to look at other form factors and other mechanisms to detect data. So this might be interesting to a different part of the room. And so this is about our work on in-ear microphone sensing that we are doing, and trying to understand if the sort of sensors that are already embedded in quite a bit of, in many hearable devices, so you already have a microphone facing inwards as well as a microphone facing outwards in many of these hearable devices. Hearable devices, I don't need to talk to this audience about it, they're very common, people use them already. In the last pandemic, everyone was there with their headphones all day, so they're really important devices. And we first tried to monitor behavior, so activity through these devices. And here is a graph. In the first two rows, it's the effect of an accelerometer detecting walking, running, drinking, other activities when the head is still, so when I'm just there and I'm doing this activity, and when the head is moving. What you see here is that for some of the simple activities might be simpler. For these, you might need more complex signal processing. If you want to detect it, it might not be working either. And these two are the same actions with the outer ear microphone. So there's an external microphone this year. Can that be used to detect any of this? The answer is not really. As soon as the head moves, this is quite affected. It doesn't understand anything. When the head doesn't move, there's no signal anyway. So the idea of our work in this area is to exploit this concept of occlusion effect. In essence, is putting a rubber in your ear means that you have created a sort of resonance chamber here that increases the higher frequency and increases also the lower frequency so that they can be heard better in this area. And in particular, the vibration of the bone conductance of the body when we step can be heard much better. And so here I'll give you a little video of what's happening. Oh, sorry, first I have to say that to do these experiments, we had to build our own very, very primitive prototype because the current hearable, even the multiple hearables don't allow us to get the raw signal, unfortunately. And so here is my collaborator Dong walking around the room with the laptop. And here you see the graph. So the red and blue lines are the inner ear in left and right, and the outer ear microphone is the green one that doesn't detect anything, but you can see the detection of the steps. Every time it steps, there's a big spike. So this can be easily detected through that signal. The other thing that is interesting is that this can also be used for gesture recognition. So wherever you tap somehow, there might be a different level of signal that can be used to perhaps, it could be a new user interface mechanism. And it can be easily detected. And if you remember those graphs at the beginning, you can see that when you don't move the head and when you move the head, you have, if you do pattern matching, they're very similar, right? So we don't need to do much signal processing. We already have the signal for this kind of activities. So what can we do? What have we tried? We've tried step count, we've tried gesture recognition, activity recognition, we've done user identification, I won't talk much about that, and we're doing heart rate detection. And so this is the performance from the activity recognition paper. Let's start one graph at a time. So left right earbud, fused earbud. All you see is that these go higher. So when you have a higher, when you have two channels, when you use left and right, our classification of the task, and the orange and the blue are just two different classifiers, they get better. So that's expected. You have two channels. So let's use them. Confusion matrix, white, black in the middle, means of the activities we tried, we don't confuse them much. We are quite good at detecting the activities we've tried. I always highlight that because you can always come up with activities we can't do. So these things are step counting, activity recognition, gesture recognition. By that I mean this. And these are the performance of just using an accelerometer, using an external microphone, using our inner microphone. Head movement, no head movement, music, no music. What we see here is the step count. You can probably do very well with the accelerometer already. Activity recognition, possibly you can do better with some more signal processing, I would say. But as soon as the head moves in this position of the body, the accelerometer doesn't seem to work as well. Gesture recognition, obviously, doing this, the accelerometer is not good at that. So this is kind of interesting. Outer ear microphone doesn't work very well. Here we're doing quite well. I'll give you a breakdown of how well this is. I like this graph because it's kind of realistic. So here are 31 subjects, activity recognition performance. So does it work well for every one of our subjects? The answer is no. So subject 2, I don't know what subject 2 is. I always wanted to ask my researchers. In theory, in ethics, they're not allowed to tell me who it is, but I'm very, very curious about why this happened. These are precision and recall. For this person, the method did not work very well. So what do we do about that? If you try to, the reason why you wouldn't, our intuition is that the method doesn't work very well because people work differently, maybe, right? They do things differently. And so what about if we feed some personal data into the model as well once we've trained the general model? Does it improve performance? And here, this green colors here is when we add a 10 sample to the class, and this goes up to 90 already. So Adi, I don't know if you can see the color, but essentially I would concentrate here. This is called purple and green. If you add 10, you go up there. If you just look here, the spike is here. So to get 90%, you need about less than 15 samples per class. And one would imagine that you could try to get her by asking the user to perform a few sample things. And at some point, you had someone going around with a magnetometer. The other way that I'll get there, the other thing that I say here is that we only have data for 31 users. No matter how good our machine learning is still 31 users. And so we think that this possibly with a large scale training with more users, this problem might just go away without doing this, without trying to do this thing. So there was a question.
Yeah, so you said that adding 10 samples per class, then you add up in the center. So is it the left one and the center one is basically the same, but just in the center you have 10 samples more per class? Is that what you said?
Yes.
That means on the left side is very few amount of samples.
So the left side, this thing?
Subject 2, yeah, you said it.
No. They have all the same number of samples.
But then you go to this figure. Yeah. So basically, okay, and here you have added 10 samples per class, and then it goes up like that. Okay, this was just one.
Did I not? Sorry, what did I miss? No,
I just was surprised. Okay, that means that on the left side you have just very, very few samples, I guess.
Well, we have 31 users, and we asked the users to do some activities for 1 or 2 minutes, right? So how much data is that? But they all have the same amount of data.
Yeah, okay.
So it's not that for user 2 you have less data.
So it's a leave one out, the left one.
Yes.
Yeah.
Leave one out subject.
Yeah.
Okay, so when you predict subject number 2, you have no data about number 2 in your model.
Correct.
So
Yeah, sorry, I should have. Yeah. It's a leave one out study, of course. Yeah.
So it's not really for the subject, but just you have not enough data to describe it. So if you take more data, then you can still describe it further.
I think you seem to have enough data for other people.
Yeah, okay.
It's just this subject, I think, is a bit on the boundaries. So it works maybe more differently than the other group. I think that's the only explanation. So you can solve it two ways: personal data or adding more general data so that you have enough variety in the population to represent also this user. This is my explanation.
Thank you. So maybe did you check whether the sensor positioning was?
Yeah,
really
we tried that. The big issue,
Position,
absolutely. There's that ear. I've learned a lot about ear canals. They're all different. We are all very, very different. And I remember doing the experiment, and mine wasn't fitting at all. I had to keep putting it back in. There are lots of problems, and we probably didn't have the best prototype. There's so many problems with this. But I think this is literally, it works. I think here is, it has worked even for us. That's what I'm telling you. Despite all this, we managed to make it work. So does it mean that as soon as you start doing some optimization of all of this, having more data, this is very promising. Case recognition. We all work differently. Can we recognize that? This is the same person with various cycles of steps, very aligned, different people, all over the place. So can we use it to recognize if it's, if you could use it for authentication, perhaps, start considering that. And because I think I'll present this and possibly not go much further, but I told you that I think we can do a lot on device, but these devices are quite small. So how much of this learning we can do on a device? We didn't have a device, we just used a Raspberry Pi. And we tried to run just the Raspberry Pi without anything on it, just record the microphone. Just record the microphone, do some gesture recognition, try 2 different classifiers, with regression, STM. And the power draw of a very non-optimized Raspberry Pi, which is a bit bigger perhaps than what you would fit, is not that big. Latency. Just doing pre-processing, doing feature extraction, and doing the inference. The feature extraction is what takes most of the milliseconds. Running the inference is very quick. And so we tried one other thing, which is performing gesture recognition every 2 seconds, which is very much aggressive, right? Every 2 seconds gesture recognition, and the device lasted 15 hours. So is it feasible? Does it give us an idea that we could try to run this set of models on device? Possibly, yes. I won't talk much about this, but we also tried to compare what happens if we start sending features through Wi-Fi and Bluetooth away instead of running everything on device, how much data you can send, and we have all these numbers, but I'll skip this part and refer you to it if you're interested. And I think for the last 5 or 6 minutes, I will concentrate on one thing that I think is very important. And I mentioned at the start, the accuracy when you talk about behavior might not just quite be enough. And there is one other aspect, which is uncertainty of the prediction. And I hear from the questions from the audience that this is a concept that perhaps you already know a little bit about. But here's a paper that I like citing, and that there are a few that since then have been published. This approach uses just deep neural network for the detection of diabetic retinopathy on images. And it's also mentioning every time it does a prediction, it monitors accuracy, but also monitors the uncertainty of the prediction. And if the uncertainty of the prediction is high, it's sending back this sample to a doctor for further inspection. And I think here is a good example of, all these clinicians are very worried that machine learning is going to substitute their jobs. And I think we are in no danger of it. I think it's more like machine learning can help them do a better job, perhaps with a simpler task. That's where I think this sort of things can help. Now, the issue is, yes, we can compute uncertainty on all of our activity recognition tasks and behavior tasks, but can we do this possibly even on device and online? So uncertainty estimation, for some of you that know this thing, mean transforming the concept of a point prediction into a sort of distribution prediction. And there are two ways of doing it. One is sampling to Monte Carlo dropouts, where you're running a stochastic network multiple times, or even if you don't understand, you understand the concept, or an ensemble method that it requires retraining multiple times. In either way, it's either if you do it in parallel, you have a memory bound issue. If you do it in sequence, you have a latency issue to solve. And so one of the things we've done is trying to see if we could run an uncertainty-based predictor for convolutional neural networks, which is something that people want to use on this sort of devices a lot. The idea is that we essentially generate this sort of stochastic convolution that we need all in one pass. And therefore, you don't need multiple passes, which if you can do it in one pass, you're able to really be quick in doing it. You don't need much of computational resources. And okay, I'll skip this one. This is about the performance. The performance are quite good with respect to the rest, but I think I'll concentrate on the systems performance. So the performance say that we have reasonable accuracy on the method, and the system performance on various devices say that we can, this is the model here. So latency is low, energy is low. The other low models are unable to match our approach in terms of accuracy and uncertainty estimation. So the trade-offs work well. So we can write on device still with reasonable performance. And I think I'll rather stop here after I tell you what we have talked about. So I think we need to improve the way in which we use sensors on a new generation of devices and in free living environment with limited label. We need to improve all those models and those sensors. We need to go beyond accuracy because if we want to use it for behavior and health, it's very important that we do. And we do need to talk about on-device and system and network performance, so the efficiency of the system, especially because some of these devices are becoming smaller and smaller. So we're not talking phone, we're not talking watches, but we start talking, my colleagues are thinking of things you put here. We're already in ear. How long until we try things more attached to the body, and that performance and the kind of what's the collection of network that this device is composed of. It could be this device and another small device attached as a computation. So we need to look at these sort of problems which are generally not looked at in the machine learning tool. And so then, of course, I would like to thank the group because it's them who is doing the work. It became quite transparent from some of my answers. I don't remember the student tried this. That's because I haven't done the experiments they have. If they were here, they probably could answer the questions much better. So thank you to them. And I'd be happy to have 10 minutes conversation about things.
We can get some questions from that. So, I don't know.
Thank you for this presentation. Like, I have two questions to you. Like, I use the eSense wearables from Nokia Brilliance. That time I saw when we tried the head movement data, then like general activity understanding time, accelerometer, and with gyroscope data, it is like misclassified with talking and eating, these kind of things with like simple model. So my first question is like, have you ever tried with these wearables to understand this kind of simple activity understanding research? And the second one is like, it is like a general question, like for behavior prediction time, like we are, this is mainly based on prediction, behavior understanding time, like which may be accurate or inaccurate. So my question is like, when we understand human behavior, that is very much person dependent or personality dependent. So how we will generalize our model to say that whether it is only accurate or inaccurate, this kind of results, through these results, how we understand human behavior in a process.
I think there are two excellent questions. The first one, are you asking if by using the in-ear microphone, we tried other activities?
Yeah, like head posture activities we tried, but in our result, we could not improve only accelerometer and gyroscope data to improve the general activity like head shaking, eating, and talking, this kind of activities.
So I think we detect speaking because this is an ear microphone, right?
Yeah.
So speaking is easy.
Yeah, speaking is easy, but speaking and eating time, it was like, yeah, I could not separate that. Those.
I don't think we've done a full study on that. I imagine the separation of the two because of the movement of the jaw might be more.
Yeah, this muscles movement.
Yeah. No, I don't know if we tried. We probably did some tests. They probably did some tests. I don't remember the results of those. So
Okay.
I can, if you send me an email, I can answer.
Okay.
But we don't have anything published on that. So the second question is, I guess if I understood correctly, is how personal you predict something that is about behavior of someone, and obviously that number is very specific to that person. Is that the question? And how do you get beyond that?
Yeah. Like my understanding is how we can generalize everyone's behavior with simple, accurate or inaccurate results because they are very much.
So in the cases, I always like to specify, like, I think you're right in some cases. In the case of detection of activity, as long as you have enough variety on the data, I hope that walking would be the same class for like that behavior is very specific. But for some of the tasks, it's easy. Now, and I imagine there are parameters, things are your question with life.
But my thinking is like I saw your uncertainty quantification thing for human behavior understanding time. So like I understand that when we collect human data and try to help clinicians to have monitored human behavior through those data, then they are also confused because patient data is very much dependent based on person to person. With simple heart rate data, even it is like very much different. So how we can generalize our model with this kind of data?
So one thing that we've tried for a different project, I'm not going to talk about that, is that I think the model uncertainty on some data might be completely different on the model uncertainty of a clinician because they use different features, in fact, to pick up things. And that might be what helps. If the model is very uncertain, maybe the clinician will have an easy task on this data because for them it's obvious, it's just features that can be picked up by some model things. So that's what I'm hoping in combining it. We've seen it true for some other audio data. Tried this test. So I think there's an avenue there that is promising. I don't know if I'm answering.
Okay, yeah,
it's a very, very difficult question.
Thank you so much.
Mr. Hall, you got
Just a brief question on the first. You were using unlabeled data for improving the models, and maybe you said that I just. So did you compare this also to use augmentation? So how does this? So do we actually need this? Can I be
Yeah. No, we tried augmentation based on transformation only, and that was working very well, as you can see in the graph. Again, I can come back to the graph and you can go to data. So transformations were working very well, and that's exactly what I was answering to her. I think there was an aspect related to perhaps that we kept only the labels that were we only kept the data that was very similar in our teacher model. And therefore, it's the transformation that had a good contribution there. So that's the kind of augmentation. The transformations were just flipping data, noise added, which is maybe augmentation based on noise. And I think we use some negation. Does it answer?
Yeah, so basically it helps to have this unlabeled data on top of.
It did help.
Yeah, okay.
But I would have expected more.
Okay.
So I think I'm happy with that result, but it was not groundbreaking improvement with respect to transformation. Transformation did help.
If the class space or the label space, or how we would call it, if it's very dense, then I guess it becomes difficult.
Yeah. I agree.
Thank you for your nice presentation. So my question is, how you prefer to have the ground truth data when the data are unlabeled?
How I prefer to have ground.
How you prefer to have the ground truth data when the data are unlabeled?
The data is unlabeled, so I'm not sure there is ground truth for that data, right?
When the data is unlabeled, is there any ground truth data in your case?
not for the unlabeled data. So there was ground truth on the small data, so the HAR data that I had, there was a labeled data. But the idea is how to improve performance of that, being that data very small. Because
that might be related to some problem. How do you choose the initial level data?
How do I choose the initial label data?
Yeah, what is there any practice to choose the initial?
No, I mean, we tried to, I really just openly, the community was working on benchmark data set that had labels. And we know that labels are difficult to get. We know these data sets are small for that reason. And so how do we improve the performance on that by using something that is possibly Google and Apple have plenty of this data just from me today. How do we use that? And they don't have any labels because the data just flows in. It has just accelerometer, no labels. So how do we, is it possible to leverage this large amount of data to improve the performance on things that we want to understand more of in a community? I think there's another question that is very related, and there's a community of work trying to say, how do we label the Google and Apple data, right? But I think it's a follow-on on this somehow.
There is a question from the chat.
Really?
Yeah, can you read or should I? Okay, what do you think about the self-supervised learning on edge devices? Will it be, yeah, so self-supervised learning on edge devices, will it be computationally efficient?
I guess you would need to perhaps use the pre-trained data and the pre-trained models and see if you can come up with pre-trained model that's small enough to fit so that you can then use some of the data of the user. I think that's what they mean, to augment that process. As it stands, I think it depends on which devices we're thinking, but I guess some of our colleagues in Georgia Tech have ported some of the devices into smaller. If they're pre-trained model, the inference on device is reasonably okay. The problem would be that we don't yet have, as far as I understand, a good way to train on device. The community is still working on device training. So if you need to you need to fine tune this stuff on device, I'm not sure how much you can push this forward at the moment.
Yeah, thank you.
Some devices.
Yeah, the last question.
Thank you for the presentation. About the earlier slides that you're using the heart rate, resting heart rate. So what's your outlook towards the use of those kinds of data that are considered proxy data from the wearable devices versus the traditional ones that are being used in activity recognition, such as accelerometer and those data?
So it is I'm not sure I'm answering, you can then ask me another question, but it is quite well known from doctors and epidemiologists that resting heart rate is an excellent predictor, and heart rate is always a very good predictor. So if you can collect that data, then you saw in all our models, every time we looped in the heart data, the performance too went up for these cardiovascular fitness models. From the accelerometer, you could, our approach said there is some signal, but it's better if you have that. And we consider that getting a resting heart rate is a very simple measure. You don't need labels for that. If you have a device that has the right sensor, getting a resting heart rate is simple. So that could be something that we know we have. I'm not sure I'm answering.
Yeah.
Okay, so it's about time. So it was very nice talk, Cecilia, and before thank you to her, but we have a gift to you. So program chairs, please come. Stefan.
We have a tiny little gift.
Thank you.
We'll be here until after lunch, so we can also catch her up.
Oh no, just come and call.
Okay, thank you very much for this session. Thank you. Yeah.
Samsung. Is it yours?
Oh, did I take your chair? Yeah, sure.
So please.
Okay, thank you very much, Professor Cecilia. And thank you everyone, all the researchers, professors, students from the ABC community. Today we have a smart city research group networking launch event. Actually, it's only a launch event. We want to just go to the networking. But while we are waiting for the launch in half an hour, we would like to introduce some activities of our members, which I have invited from the ACE, the School of Architecture, Computing and Engineering, UEL. Smart City Research Group is a multidisciplinary group because our school includes architecture, computer science, as well as engineering. So that would be a very good opportunity for us to encourage some multidisciplinary projects inside that. Usually we have monthly talks between us, but for this month, I have invited my colleagues to come here to have a joint networking event with the ABC community. So first I ask Dr. Ahad to start, and we will have Dr. Amir, Dr. Fahime, Dr. Mohammed, Dr. Sujit, and other my colleagues to come and talk about their work for 3 or 4 minutes. Thank you very much.
Thank you very much. Welcome to this short presentation. So this is about research related to smart city. So I am here presenting some of the works that is related to smart city. So what is GATE? So what we did, this work is now working with Toyota, that if we can understand that from the walking people, which we call GATE, to understand the person from a car. But when there is a car in the city, we have occlusion. So how to deal with occlusion? So we work on this. It's very difficult. And definitely we need large data sets, really large data sets, but there is no large data sets on occlusions. So we created artificially, occlusion patterns are created artificially from 10,000 people, and then we work on that. This is one. Another one is that we collected the data in Tokyo Museum based on sensors to predict from the city people or shopping center, wherever they are moving, age and gender for different security perspectives, as well as, of course, business. And another one is WIO, Sussex University's WIO, Sussex Locomotion Transportation Dataset. For the last 4 years, we have been working on this challenge, and last 4 or 5 years, in fact, and then we achieved 2 awards so far. So over there, what we try, that different kinds of transportation modes, so not human, but what kind of transportations I'm using, so that we can go for different kinds of, context-aware prediction. So that was this works, this kind of works, everything, what we published exactly related to that. So this is about understanding the different kinds of transportations and so on. We can't see the title, but it's just like sensor data. It's fine so far. And the next one is location and information and transportation from radio data. So from the mobile phone, if you have different kinds of location and reception and other information, can we extract those information to understand various context-aware services, like traffic information and localizations and routes. This is another work where we wanted to understand the gait, the walking pattern, and the attributes of the person. So attributes like my walking is relaxed walking, or I'm juggling, or I have some problem or something like this. This is a very unique work we have done, and on very large data sets at the same time, and real data set that based on the walking pattern, can we understand the attributes and behavior? Those things are very much useful for security and surveillance in the city areas. So definitely we have basically 3 to 4 minutes per person. So I'm very quick, only 2 minutes I have taken. So I mean, there are lots of works and scopes in a smart city domain based on human activity and behavior, but what kind of sensors you can use, like RGB data or depth or skeleton. Outdoor, we can consider RGB, but not depth and skeleton because it's noisy, or we can use different kinds of environmental sensor or on-body sensors. Many applications we have done so far. I didn't mention everything, but healthcare, rehabilitations, autism, and security biometrics. And what is most here is that evaluations and predictions based on the current situation. So that's it. I'm thankful to my collaborators. I think we don't have time for QA. Next presenter, please. And then during this lunchtime, we can discuss. So please enjoy your 3 to 4 minutes maximum. Thank you. Nobody presenters don't say that 3 or 4 minutes very quickly. They try to keep more. But as I am part of this, so I really try to make it maximum 4 minutes so that we can. Oh.
Yes, exactly.
Yes. Okay. Yeah. Okay. Thank you very much.
I think you still have 1 minute, so I will go. I use 1 minute. I would like first of all to welcome you to University of East London, and really pleasure to see you here. The work I'm gonna just, as I said, we have 4 minutes each just to give you an idea about our work here in the university. And I'm gonna talk about something called chip of forensic. Have you anyone familiar with digital forensics here? Okay, brilliant. Just would like to show you some. Let's take this out. We have what we usually do in terms of in our laboratory downstairs. We do we are interested about reverse engineering research and techniques. We have like a damaged device here. We are really interested to get the chip of that device, whether this device is really burned or broken or damaged in any way. And this is mostly came from digital forensic investigation cases where the police and law enforcement are involved. So that we got the device, and our first mission to get the chip out of this device. In order to do so, we have to do some of the hardware or some of the hardware tools, and at the same time, we're trying to clean this. We're doing like what we call it, getting the we call it decapsulation process, and we use gases and chemical materials to decapsulate the packaging, and in order to get this one. After that, we do again some of cleaning and like plasma etching, and we use again some gases like oxygen, O2, fluorine, and nitrogen as well to clean. And when we reach to that level, we try to expose the dyes, the connected of the chip itself. And sometimes we are lucky. We will find the bonding is still working, absolutely no problem. We evaluate, we test, and if there is any connection, then we will try to get the data at this level. But if there is no connection here, then we have to do what we call it a probe. We try to we go to rebonding. We reconnect the wire, the golden wire of the chip itself. And here we talk about micro. And the hair size is really impressive to compare to the die of or the wires of the chip. If there is after we do rebond, then we try to probe and try to connect to get some of the result. Here is what's a probe actually what we do, which is exactly, this is really very hard a process and really has to be precise. And at this same stage, for example, while you are working at this level with the microscope, trying to connect maybe someone passing by, then you lose all the connection. Then you spend another maybe half an hour or 30 minutes to get into the needle into that dot where you can connect. Of course, here just very quickly, as I said, I don't have, this is very as well another picture, but here I would like to show you, for example, here this is with O2 SIM card. We got the SIM card, then it was no really wiring. We'll reconnect here, for example, and then you will see that we manage to get the data. In our process, we try to do, when it comes to reverse engineering, we try to develop any techniques which require less time, less effort, but will give you the same result you aim at the end, that to get the data out of the SIM card. So this is general. Here's some just a quick example. I got 2 minutes. Yes, I got just this here. And here, as mentioned here, exactly what we're doing down there when come to the probing the SIM and getting the data out. Sometimes, you know, maybe you don't get all what you wish, but sometimes maybe you start conversation in terms of any type of data connected to this. So thank you very much for that. Yes, I'm on time, yeah? But we have the lab downstairs. If you are really interested, more than happy to show you around and explain a little bit more if you are interested in that. Thank you very much.
Thank you. Okay, may I ask Dr. Amir Hosseini, these are just very short presentations as a seed with my colleagues. Thank you. Can I put the slides? Sure.
Hello, everyone. It's a great pleasure to be here with you today. I'm Dr. Mohammad Hussein Amir Husseini. I'm a lecturer in computer science and digital technologies at UNIL and the course leader of BSc and MSc Digital Technology Solutions apprenticeship courses. So today I'm just going to introduce 3 international large-scale projects that I was involved in, and talk about a little bit, my research-related, AI-related activities. So when we talk about smart cities, obviously there are security, education, mental health, and mental well-being. So the first project I'm going to talk about is Spirit project, and it was mainly focusing on using artificial intelligence techniques for identity. So it was a Horizon 20 European project. The project was getting 5 million euros fund from European Horizon 2020, and 9 different European countries were involved, including Spain, Belgium, Germany, Greece, United Kingdom, Sweden, and so on. And the consortium was including 17 different institutions, including some of last developments and representing the UK as one of the senior researchers in AI aspect, and I was responsible to develop the AI models for identity resolution, and some of them are end users. So for instance, in Greece or metropolitan police in the UK, they were using the product for doing identity resolution in the real world and providing real evidence, reliable evidence for the court. So this was one of the projects. The other project is related to psychology and the application of machine learning in psychology. So the core of this project is going back to my PhD project when I was using artificial intelligence to automate neurolinguistic programming, which is a psychological method for personality development. So I developed 3 bespoke AI model for personality prediction, identification of preferred representational systems and learning preferences in people and other aspects in order to use it in organizations to improve the organizational performance. So we commercialized those 3 bespoke AI models in this project. So I was collaborating with Winus company and we applied for an Innovate UK smart grant funding, and we got 100,000 funding for this project. So the final product is an application, AI-powered mobile application called Winus that can be used by employers, students, companies and organizations, and universities, and it will help the user to go through a conversation with the app, and the AI models will do some prediction for personality, their learning style, and they will help them to have a better self-understanding about themselves, about their weaknesses, about their behavioral patterns, their character, their personality, and try to understand their sweet spot when they want to decide about a job, or the companies when they want to do the task allocation based on the abilities and personalities of their staff. So the app was sold to many different organizations, UK-based and non-UK-based organizations, and also universities are using this product. And the other one, which is again related to psychology but is a bit unique, and there can be an application in the smart cities as well, is a project that I'm doing with University of Pennsylvania and dog vatar company, which is a startup in US in Florida. So in this project, for the first time, we know that AI has been used for psychological aspect of human, but it hasn't been used for psychological aspect of animals. So this is the uniqueness in this project, because for the first time, we are using artificial intelligence to understand the behavioral patterns in dogs based on variety of attributes, and come up with a personality profiling tool for the first time in the world. We started with dogs and we are expanding this for other animals as well. So a zoologist professor in University of Pennsylvania is providing a very large scale, including 170,000 actual samples, and each dog has got more than 110 attributes. And this is an unlabeled data set. So we are going through the clustering, we are coming up with a labeling strategy, and then based on the category that dog is going to be allocated to, we come up with a clear description about the behavioral pattern, and we're going to call it the personality type for the dog. So this is one of the project, and the product is going to be commercialized, and the dog vatar company is going to patent it, and it can be used for people when they want to adopt a dog or buy a pet, for instance. I also had some other contributions, AI-related, contributions to different international industrial and academic panels like IORMA, talking about how AI is enhancing personal development, and also some other international patterns about redefining national power in the age of artificial intelligence, for instance, which was hosted by 8 different institutions globally. And I also contributed to as a key speaker in different industrial events in Germany, Greece, Italy, Brazil, and hosted some IEEE special sessions in different conferences, and also had some TV appearances, as an expert in AI to talk about different AI-related topics. For instance, the future of the smart cities was discussed in one of the programs with some professors from Tehran University. Collaboration between academia and industry, bringing innovation and to knowledge-based startups who are working on AI-powered systems. The relationship between artificial intelligence, application of artificial intelligence in international relationships, especially about the conflicts that we have in the current world, and also artificial intelligence and revolution in media, focusing on social media engineering. So thank you very much. If there was any question, we can discuss it during the lunch.
Thank you everyone for your nice time in here. Basically, I am working blockchain and machine learning things, bridging these two things. Basically, distributed, secure, collaborative learning platform for health informatics. The basic intention of this project is, as you, I think all of you are mostly coming from the machine learning platform and machine learning field. So what we are doing in machine learning, we are collecting all data and storing in a centralized server. Then we are running on the machine learning things. So that this technology is sometimes creating so many security issues. So most of the cases, whatever we are running on experiment, mostly this is privacy preserving data. So ultimately, we are not getting always accurate result or the right prediction. So the intention of this project, that how we can remove this centralized server and we can make a collaboration with different organizations and make a collaborative learning. Where is the main slides? There is any animation doesn't work. Yeah, there's many slides inside this.
Moving. It's a PDF version. Sorry, I changed it to the PDF.
Okay, can I download? Sorry, just interruption because the animation is off. Okay, so the thing is that what we are doing in here, we are replacing the centralized server, and we introduce the federated machine learning in here. As we know, Dr. Nicholas, the first keynote speaker, he's discussed about the federated machine learning. The basic concept of federated machine learning thing is that you have your data, no need to share your data, but I will extract the knowledge from your data. So the basic intention in here, we can collaborate with multiple healthcare organizations, maybe 10 hospitals or 15 hospitals from different parts of the world. Like one is in US, another in Japan, another in UK. So these healthcare service providers like hospitals, they have individual servers. So what we can do, we'll learn in using the federated machine learning. The individual healthcare organization will train their model and then share their model to the other server. That is called the federated server. The federated server are making average of every local models and creating a global model and then running on the next step up. The challenges in here, we introduce the federated machine learning things because of to eliminate the centralized thing. We don't want to share the data, but recent research already proved that we can retrieve the raw data from the updated model. It is proved. Many research claim that thing. So whether the federated server is storing all local models, then updated model or averages model. So how we can remove this thing? So in my research, in our group, what we are trying to propose, we are eliminating the federated server and we introduce the blockchain thing in there. So ultimately, the whatever learning model coming from the every individual healthcare organization, then we are making average by federated by blockchain network. So you know, the blockchain is very highly secure technology that launches many security things and information security, and every data are secured and encrypted. So ultimately, the federated machine learning things introduce the primary security things of without sharing the raw data to the from the users or from the users to the federated server, and federated server replaced by the blockchain thing. It introduces the complete security things. That's what we are working on. Sorry for that, because I introduced some animation slides, but somehow it's not running on here. In here, you can see in here, this is the traditional network. Think about that. This is a normal healthcare service providers. They are providing, this is their individual networks, and they are providing their own services. But when we will, then after coming this, every individual network creating a local model. And traditional federated machine learning, there is a central server in here. When we are using the central server in here, if somehow the central server is hacked or managed, then every local model is going to be disclosed. So what we can do in here, in our research, we are proposing that we can replace this federated server, that is centralized server, by the blockchain network. So it can make a collaboration with the whole over the world. And as the last keynote speaker, he discussed the, also you are very familiar with this thing, the machine learning accuracy depends on the diverse of data. So if we can collect the multiple data, various kinds of data and various diverse data from different organizations all over the world, then we can make a better model. So where is our research? Our research is not so easy to us to collect every data and feed in the blockchain things and to do the machine learning, because that data is very diverse and unlevel. So how we can do these things? We are introducing some API that can make the level and can align to run the machine learning things seamlessly. So this is the our blockchain related blockchain and federated machine learning things bridging. This is our research. Thank you for everyone, and welcome for collaboration. If I can get some extended knowledge from you. Thank you.
Good afternoon, everyone. My name is Ilakshan Balasubramaniam. I'm a PhD student in the School of Peace. And my research is about the failure of seawalls under the tsunami-induced current. And my director of studies is Dr. Ravindra Jayaratne, who is a reader in coastal engineering in the School of Peace. So this study we are doing is funded by the Royal Society, and we are doing this in collaboration with University of Michigan. So talking about the tsunamis. So tsunami is one of the major natural disaster known to mankind. And after the tsunami incident in 2004 and 2011, the perception of tsunami had changed all over the world. Especially after the 2011 tsunami in Japan, we had several building failures and sea defense structures failure. So after that, what we did is the post-study, that means post-disaster tsunami surveys indicated that all these failures were happened because of the scarring in the leeward side of the structure. So we decided to investigate more into this and to propose a new model so that we can find how much scar we are getting from tsunami-induced overtopping scar. So the key objectives of my study will be analyzing the various structure geometries which are already there, and numerical models which have been already proposed. And I am going to test different geometries of seal wall defense structures like inverted T's, cantilevers, etc., and check whether the various soil grain diameters, density, and the hydraulic forces and the pore pressure, how much they are affecting the real-time time-varying spur profile. Then what I am planning to do is to verify the accuracy of the existing model using the data I am getting, and then to propose a new curve model. So these are the previous work we have done in the UEL, and we have a nice flume in the hydraulic laboratory in UEL. So we had created a dam breaking scenario as shown here. So we just store the water there and recreated a lifting gauge and created a dam breaking scenario to create a tsunami waves. And we have a structure kind of things in the other side of the flume, and we analyze what happens to the buildings when a tsunami wave hit this structure. So we have developed some score depth, some equations to calculate the score depth in the leeward side of the structure. My current research interest and the current research studies is in investigating about the different geometries which are in the sea defense structures, and we are planning to propose new square depth formulas so that we can have safer cities in future. Thank you.
Unfortunately, launch is here. It is not ready yet.
I can cancel my presentation.
No, we have 10 minutes.
No, I'm just kidding. Okay. Good afternoon, everyone. It's a great pleasure to see you here in Kenya. So my name is Dr. Fahmi Jafari, and I'm a senior lecturer Department of Computer Science and Digital Technology, and I'm postgraduate research lead in our department, and also tutor for MSc Computer Science. My research interests are big data, artificial intelligence, big data, and I started my research working on embedded system, particularly on performance evaluation in computers and system on chip, and then I work on data analysis and machine learning. And then I got interested in big data technologies, which is one of the cutting edge areas. Still my main focus is big data technology. That's why I'm involved in teaching 3 different modules in our department in big data technology, 2 MSc and 1 undergraduate. And also work in internal teams somehow related to the embedded system that I was working before. But of course, with Dr. Adi, we are designing a new MSc program in our department, which is academic. Just quickly about the research projects, I can quickly say, it was going to be animated, but anyway, so I can list 4 ongoing projects: smart road safety, smart macrogrids, fintech, which is in collaboration with the Center of Media and assistive technology. So I'm not going to explain this kind of projects because I don't have time for that, but I'm really happy to have discussion on any of these things that you are interested in. But in all these projects, of course, we have data processing, we are using different technologies, systematic analysis, machine learning, these kind of things. But what I wanted to explain is, in all these projects, we have 2 different parts: online processing and offline processing. What I'm going to explain and highlight is, for online part, you have a real-time framework using big data technology. This is the framework that you are using in our project. So you are using Kafka, collect real-time data from different sources, and then you use Apache Spark, particularly Spark streaming for online processing, and then of course after that, Sutra and streaming for saving data and visualization. This is the real-time framework that we are using for online part, which use all the big data technology. I mean, we know that big data is an important part of smart cities. So for example, when I'm talking that we are using this framework, it doesn't mean it's like the same development. Of course, for each part, we have different developments based on the project that we are using. For example, for fintech, the sources that we have as a part of fintech, the source that we are using is the social media. And of course, we have sentiment analysis for our real-time framework. Or for example, for smart cities, we have this framework, but of course, different development. The sources that we have is OpenStreetMap for location features, visual crossing for weather, location trace, and real-time traffic. And then, of course, after collecting the real-time data, we have machine learning, which has been trained offline based on the historical data. And we use that model to have an online prediction for accident risk score, which this is the online accident risk score, which is used in the navigation for finding the safest route between two points. Or, for example, in the small microgrids, we use similar framework, but of course there are some other components on top of that to collect real-time data from smart meters, from different properties, from factories, from power stations, and use the data machine learning to find out how is the best and what is the cost efficient distribution of energy. So I can't explain more because it's just, of course, 4 minutes, but I'm really happy to have discussion on any of these topics that you're interested in, and of course, my interest for collaboration.
Obviously, it's not the only research area that my colleagues have the smart city group research in our doing. Just a sample of that, I can see that the norms is not great yet. There is still 1-2 minutes for myself to introduce myself. I'm Ali Borashi, the senior lecturer. My background is telecommunication. I try to use machine learning algorithms to enhance the performance of the telecommunication system, basically. And also I have done something with the robotic healthcare things. And also I have some research on tracking and positioning, which I think is more related to this conference. So I have selected some of my recent papers just to read the name of them and the relevance to them. Then if you are interested, possibly we can discuss them. In 2020, we had the same problem that Professor Cecilia told this morning. We wanted to use use deep learning and getting the offline part of the work much more complicated, but on the other hand, the online part of the work much faster. So we moved the complexity of learning the behavior of the statistics of the system to the offline part, which can be done offline, and then try to get a much faster online portion of the classification in our work. So we published it in the expert system with application in 2022. And also we, based on this work, we improved this work to use a computationally efficient multi-target Gaussian. It was a 2-dimensional one. We extended it to more than 3-dimensional Gaussian process regression algorithm and published it as another paper, again in 2022. And also we calculated the confidence interval estimation. That was also a more theoretical part of the work, a confidential interval estimation for fingerprint-based indoor localization. And we published it in ad hoc networks. And the last thing I want to say, I am a guest editor of a special issue about machine learning, Internet of Things, and indoor positioning localization. The deadline is still open. We have 1 month. I wanted to invite all of you. If you have any paper, we would be more than happy to review it and possibly accept it for the publication in the Sensors journal, which is an open access journal. And that's it. Thank you very much, everyone. Lunch is ready, so please make the best use of this opportunity. Of my colleague and the ABC community. This is a very good opportunity to talk to each other and make new opportunities. Thank you very much.
Thank you.
One of them was nice today.
Thank you very much for coming. Thanks a lot for coming. Thank you very much.